For many years, we have always treated the moon as a static, silent rock that hasn't changed since the dawn of the solar system. Our mission plans for the next decade were built on the assumption that the lunar surface was the most stable platform in our neighborhood. But right now, that narrative has been dismantled. New data from the Lunar Reconnaissance Orbiter, combined with AI-driven seismic modeling, has confirmed a startling reality. As its internal core cools, the moon is contracting like a drying raisin. Because the lunar crust is brittle and cannot stretch, it snaps. Those fractures form thrust faults that run across the lunar surface, and they are not ancient relics. Many cut through young terrain, indicating they are still active today. Along these faults, shallow moonquakes are occurring close to the surface. Unlike earthquakes on Earth, lunar quakes behave differently. The moon's crust is dry, rigid, and lacks the damping effects of water and layered rock. When it fractures, vibrations persist. A quake that would last seconds on Earth can continue for hours on the moon. This matters because several of the most active regions overlap with areas targeted for future missions. Inside Shackleton Crater, near the lunar South Pole, orbital imagery shows landslides linked to nearby fault systems. The moon is not breaking apart, but it is not static either. We are preparing to operate on a surface that is still under stress, using infrastructure concepts originally designed for a world assumed to be inert. The evidence for this isn't coming from a single instrument or a single dataset, and that's what makes it difficult to dismiss. The Lunar Reconnaissance Orbiter has been imaging the same fault systems for over a decade, and when researchers compared high-resolution images taken years apart, they found subtle but consistent changes along several scarps, fresh debris at the base of slopes, and surface textures that don't match long-term erosion patterns, suggesting recent movement rather than ancient collapse. Those surface changes line up with seismic data collected during the Apollo missions, which recorded thousands of shallow moonquakes concentrated near these fault systems. At the time, the data was poorly constrained, and many of the signals were dismissed as background noise or thermal effects. But when modern models were applied, the timing and locations began to match in a way that's hard to ignore, especially near the lunar South Pole. What's important here is scale. The moon is shrinking far less than a centimeter every year, an amount too small to notice directly, but over time that contraction builds stress in the crust, and when it releases, it does so close to the surface. That's why these quakes are shallow, and that's why their effects can directly reshape local terrain, rather than dissipating harmlessly deep underground. This also explains why the moon behaves so differently from Earth, where tectonic motion constantly redistributes stress. On the moon, there is no such system. Stress accumulates slowly and unevenly, and when it releases, it does so in concentrated regions, producing events that are rare but mechanically intense in their immediate surroundings. And that difference becomes especially relevant when we consider where future missions are planned, because the regions of highest scientific interest are also the regions where the moon's internal stress is most likely to express itself at the surface. Previous models assumed the interior had cooled almost entirely billions of years ago, but the presence of active thrust faults and shallow quakes indicates that heat is still escaping. That heat drives slow contraction, subtly deforming the crust and altering stress patterns over time. Over its long history, this gradual shrinking has caused the moon to lose roughly 50 meters in diameter since its formation, building stress into the crust that continues to express itself today. In turn, these stress patterns influence where future faults may form and where the lunar surface may shift unexpectedly. Observations of boulder movement and fresh debris along scarps show that even small changes can have cascading effects. Over decades, repeated minor adjustments can gradually reshape slopes. For missions targeting permanently shadowed regions or crater edges, understanding these micro-scale changes is critical for both robotic and human operations. Seismic modeling now suggests that the moon's interior is more complex than a simple solid core beneath a rigid mantle. Variations in composition, cooling rates, and localized heating may produce stress concentrations in ways that were previously overlooked. This helps explain why some faults are more active than others, and why quakes cluster in particular regions rather than being evenly distributed. In practical terms, this knowledge affects landing site selection and even the design of scientific instruments. Equipment must withstand not only thermal extremes, but also surface shifts that could destabilize structures or interfere with experiments. Future lunar infrastructure will need to account for slow but persistent geological activity, adapting to a surface that is far from static. Finally, the Moon's ongoing evolution offers scientists a unique opportunity. The Moon preserves evidence of contraction and faulting over long timescales. By studying these patterns today, researchers can better understand the mechanics of planetary cooling and the long-term evolution of terrestrial bodies throughout the solar system. One of the main difficulties in understanding this activity is that the Moon has never been monitored in the way Earth is today. The seismic instruments left behind during the Apollo missions were limited in both sensitivity and coverage. They operated for only a short period and were all located on the near side of the Moon. They detected movement, but they could not clearly resolve where it originated, how deep it was, or how the energy traveled through the crust. Because of these limitations, much of what scientists know comes from careful study of surface features rather than direct measurements. The nature of the lunar surface itself also plays a role. The Moon's outer layer is not the same everywhere. Some regions are loosely packed, while others are more compacted by repeated impacts. New instruments are being designed to operate continuously and detect much smaller movements than before. They will allow scientists to connect surface changes with internal activity far more clearly than has been possible in the past. As this information accumulates, the Moon is no longer viewed as a fixed reference point, but as a body that can be monitored and studied as it slowly evolves. Its changes are not dramatic, but they are measurable, and they offer insight into how airless worlds lose heat and adjust internally over immense spans of time.